So let's talk about bonding. First, we're going to take a look at ions and ionic bonds. When we bond, we like to mimic noble gases. We like to be isoelectronic to a noble gas, i.e., we want to have the same electron configuration as a noble gas. So we can do this via sharing electrons, losing electrons, gaining electrons. So we've got a few different things that happen here. We have what's called the octet rule. If we look at our noble gases, they all have a complete octet, meaning that we have 2 s electrons and 6 p electrons for a total of 8 electrons. Except for in period 1, where the only orbital we have available to us is that one s orbital. So hydrogen and helium go after a duet instead of an octet, because we don't have any room for any other electrons. Okay, so when I look at my metals, they are going to lose electrons, they become cations, and so they become isoelectronic to the noble gas in the period previously. So if I look at my period 3, sodium, magnesium, aluminum, they will all lose electrons to have an electron configuration identical to that of neon. Okay, my nonmetals, they are going to gain electrons, and they are going to become isoelectronic to the noble gas at the end of their period. So something like phosphorus, sulfur, chlorine, they'll gain electrons until they have a full octet, making them isoelectronic to the noble gas at the end of their period, which is argon. All right, and so we do have 2 modes of bonding. If I have a metal and a nonmetal, or a metal and a polyatomic ion, I get these ionic bonds. We're held together by an electrostatic force. We gain or lose electrons to form that octet. Or we have covalent bonding. That's where we share electrons. This is primarily between 2 nonmetals. And so they share electrons, and that forms their octet. We'll talk about covalent bonding in a different section. All right, and so we know that cations, we've lost electrons, anions, we've gained electrons. Okay, and then we're removing electrons from the highest occupied orbital in a cation, and we are adding electrons to the highest the lowest unoccupied orbital for an anion. And then transition metals, we take off the s electrons first before we mess with any d electrons, because those s and p electrons are the valence electrons. So I can look here, and as you see, when we make aluminum an ion, we have a full valence shell. When we make sulfur an ion, we have a full valence shell. So again, what are they trying to do? They're trying to be isoelectronic to one of those noble gases. So sodium, if I take off its single 3s electron, it has a 1s2, 2s2, 2p6, just like neon, so it's isoelectronic to neon. Fluorine, if I add in one more electron to its electron configuration, now it has a full octet, and it is isoelectronic to neon as well. So again, isoelectronic just means that they have the same electron configuration. Okay. Now it's really interesting when we look at the size of our ions. Our cations are going to get significantly smaller. So there's 2 things happening here. We're taking electrons off that highest occupied orbital. So in the case of like sodium, we have a 3s electron. Well, I take that off, and now I'm isoelectronic to the previous noble gas for 2 reasons. Now I've lost that electron, I have that same electron configuration, and we get smaller because now I've lost something from a bigger orbital, and I have a higher effective nuclear charge, because cations have what charge? They're positive. So now I have an uneven distribution of positive and negative charges. So I have a lot more positive charges in my nucleus, which yank the electrons in a lot closer. Our anions, we also get an uneven distribution of charges there, but we're also crowding more and more electrons into the same shell with the same number of protons, so it causes it to swell. All right, so you can see here, in gray, I have my neutral species. In maroon, I have my cation, much smaller. In gray, I have my neutral species. In teal, I have my anion, much larger. Okay? So you can see there again, our cations are going to get smaller, our anions are going to get larger. Right? And now, when we make our ionic bonds, these are held together by electrostatic forces. And so we need ratios for our ionic bonds that give us a neutral species. So if I look at something like sodium chloride, I have a sodium ion, I have a chloride ion. We know that sodium forms a +1, chloride forms a -1, and so we get NaCl as our formula there. Okay? We can look at these Lewis electron dot structures to understand what's happening with the electrons, though. So here I have potassium and chlorine. Okay, so we know that potassium likes to form this ion, and chlorine likes to form that chloride ion, and we get. Okay, so what's happening with the electrons, though, to achieve the octets? Well, let's see here. I've got my potassium, and I've got my chloride. All right, so potassium forms a cation, so it loses the electron. Chlorine forms the anion, so it gains the electron. So this electron from the potassium is going to get transferred over to the chlorine, and we're going to get something that looks like this. Okay. All right, so they each have their octet, and then we finally get our formula KCl there. Okay. All right, I can do the same thing with magnesium and oxygen. So we know that magnesium does like to form that +2. And so we should get an MgO as our ratio there. So we'll pair. Okay, so my magnesium ion. My oxide ion. And there's my magnesium oxide. Okay. All right, now what's happening with sodium and sulfur? So we know that sodium looks like that, and sulfide looks like that. When we charge balance this, we get a formula that looks like that. So how is this going to work? Well, for it all to fit together, we're going to need 2 sodiums. So we're going to do this. Okay. So that'll go there. That'll go there. Okay. Our sulfide. And there's our sodium sulfide with the 2 sodiums and 1 sulfur. Okay, we'll try one more. All right, we've got this calcium and chlorine. So calcium makes that +2. Chlorine makes the chloride with the -1. When we charge balance that, we know our formula looks like that. So what happens here? Okay, we'll take one there and one there. Okay. All right, and then that's where we get our calcium chloride there. Okay, so that's how we can use our Lewis electron dot diagrams there to show where all these electrons move around to as we put those charge balances in together. And so we see that it does indeed go together in the same way that we've been writing our compounds all along, but now we see where all those electrons go. Now with our ionic compounds, because they're held together by electrostatic forces, these guys will crack when you whash them with a hammer. Because if I have positive, negative, positive, negative, positive, negative, that's going to hold together. That's a good alternate charge. If I smash things though, well, what do we know about positive and positive or negative and negative? Well, they repel each other. And so when I smash it, I line those up and they go pop and they come apart very easily. Our ionic compounds also conduct electricity when they are either molten or dissolved in water, because to conduct electricity, we need mobile charge. And so if I have cations and anions, if I melt them, now all of those are moving around, my light bulb lights up. If I dissolve them in water and I completely disassociate all of the ions from each other, now I have the cations and anions floating around in water, and so my light bulb lights up and we get conductivity. This is why hair dryers have warnings on them that say don't use while you are standing in water, because our tap water has dissolved stuff in it. So it has ions in it, so it has mobile charge, so it will conduct electricity.